In this tutorial, we'll be learning how digital audio works. While this might seem theoretical, I guarantee that the more you understand about how the stuff you hear turns into digital binary code, the better your work is going to be. First, let's talk quickly about the energy and electronics involved. You start, of course, with a sound. Something that disturbs the air and generates sound waves, your acoustic phenomenon. Next, you need a transducer to convert this acoustical energy into an electrical signal, a microphone, for example. Finally, somehow you need to store these voltage variations produced by the transducer so that you can reproduce them afterward. With analog recording, like tape recorders, an electromagnet realigns magnetic particles on the surface of a moving tape. This varies the intensity of its magnetic field in response to variations in the incoming voltage. That's how the electronic version of sound waves gets stored. The magnetic stuff stored on the tape is converted back to voltages through the amp and speakers. The result is fairly analogous or similar, hence the name analog recording, to the original signal. As you can see, recording sound is a pretty complex translation of energies. Recording sound is a real-time chain of physical components that directly convert energy from mechanical form or acoustic form to electrical form to magnetic form and then back through again to your ears. Digital audio recording works differently, very differently. Digital audio is computer data that represents audio waves. That's what's meant by digital, where something you hear in the real world is converted into numerical form, binary digits. Digital audio is not sound. That's one of the reasons why audio processing and monitoring is so resource-intensive on your computer. It has even more energy conversion steps than analog recording. The input signal from an analog source like a microphone arrives at an analog to digital converter. That's your sound card or your DigiDesign interface. This converter periodically measures the level or amplitude of the incoming audio signal, and these measurements are then stored as binary numbers. In order for these binary numbers to get back to your ears in the form of sound, this entire process gets reversed simultaneously. Okay, first let's talk about sampling. To convert audio to digital form, we use a process called sampling. Computers capture samples of the voltage of audio at fixed time intervals, i.e., they capture the product of the transducer like your microphone. These samples are stored in files as binary numbers. The number of samples per second is called the sample rate. According to something called the Nyquist-Shannon sampling theorem, the sampling rate needs to be twice as high as the frequency you're reproducing. The human hearing range tops off at 20 kHz, hence the 44 kHz standard sampling rate on CDs. In this bottom graph, the waveform is captured twice per period. That's what the red dots mean. Even though the sample points don't exactly match the highs and lows of the period, the frequency is still accurately represented in the recording, but the volume in this case will be a little bit off. Now, what happens if there are fewer than 2 samples per period? As we see in this graph on the right. What'll happen is that the original high frequency gets lost and a new low frequency gets created. This is a nasty effect and it's called aliasing. It's basically bad news for your recordings. But the good news is that your software and hardware do have some built-in algorithms that prevent this from happening. The sample rate of conventional audio CDs is 44,100. That's normally referred to as 44.1 kHz. 48 kHz is the standard sample rate for videotape formats, as well as camcorders. 96 kHz is the standard sample rate for DVDs. Some versions of Pro Tools let you choose the higher sample rates for your recording, but keep in mind that the higher your sample rate, the larger your files are going to be and the greater the demand on your computer. Until not too long ago, 44.1 kHz and 48 kHz were the most common sample rates for professional audio applications. Pro Tools M-Power supports some higher sampling rates, and HD, as well as some of the LE versions, support up to 192 kHz sample rates. Next, we're going to talk a little about bit depth. Another property of a sound wave, when converted to digital form, is its bit depth. Bit depth refers to the number of binary digits in each sample. The higher the bit depth, that is, the longer the number, the greater the dynamic range of the audio, that is, the difference between the softest and loudest passages. The longer the binary number that stores the sample, the more true or accurate the digital representation of the sound, and the less quantization error you will have in the binary numbers approximation of the sound wave. Most commonly used are 8-bit, 16-bit, 24-bit, and 32. Each bit gives an additional 6 decibels of dynamic range. When we talk about these possible amplitude values, we're speaking exponentially. The bit depth is a figure of 2 to the power of 8, 16, 24, or 32. 8-bit is commonly used on the internet to keep your file sizes small. It gives you 256 possible amplitude values, or 2 to the power of 8, and a dynamic range of 0 to minus 48 decibels. 16-bit depth gives you significantly more amplitude values. 2 to the power of 16 is 65,536. 16-bit depth gives you a dynamic range from 0 to minus 96 decibels, so your pianissimos will be really quiet and your loud sections will be really loud. 16-bit depth is CD quality, and the recordings you export from Pro Tools onto an audio CD should be at this bit depth. 24-bit depth recordings won't play on standard CD players. 24-bit depth, or 2 to the power of 24, gives us nearly 17 million different amplitude values and thus a much greater dynamic range from 0 to minus 144 dB. 24-bit depth is the standard for DVDs. Because of the significantly larger amount of data involved when you record in 24-bit, you need much more storage capacity on your hard disk. 24-bit tends to be the default for input recording these days, even though you'll convert to 16-bit for audio CDs. It's generally thought that due to the limitations of human hearing, 24-bit depth is sufficient for audio recording. You can record in 32-bit depth, or 2 to the power of 32, but you will need much more storage. This bit depth offers more than 4 billion possible amplitude values and gives us a dynamic range of 0 to minus 192 decibels. This is, of course, resource intensive, and Pro Tools M-Power doesn't support this. Many of the LE products don't support this either, but Pro Tools HD will. And this concludes our overview of digital audio basics.